also include. So that means we should also include this extreme climatic events on ecological composition change for our conservation strategy, right? And also we know that these conservation strategies are not same for freshwater and also for terrestrial, because one recent study also recommended to include the prioritization area which can focus on both freshwater and also on terrestrial needs. So we need something to detect that how community stability is changing due to these extreme events across the realms, right? And so the concept of stability, that is this table I took from this paper, which is a Nature review in 2000, and it is showing that different concepts of stability is used in ecology, and mainly the first concept is the equilibrium stability or the general stability. That's mainly for analyzing different time dependent models, or more qualitative in the sense, like if you have your system in a equilibrium state, that means there is no variability in absence of any perturbations, and then you give a small perturbation. So again, if the system can come back to its initial state, that means your system is stable, that equilibrium is stable, right? But actually empirical ecologists, or more the ecologists in the field, they use the variability concept more. So variability is like that how much variation in the population density over time. So if you have a more variable community, that means more fluctuation in your total productivity throughout the time. That means that your community is less stable. And this variability is usually measured as the coefficient in variation. And we will focus on this concept for our study. So we measure that stability as the inverse of variability, right? And that means variability is like that how much standard deviation of your total community biomass with respect to its mean. We use that interquartile range and median for a non-biased estimator. Now the other concepts here is like the resilience and resistance. Those are also used for stability, but mainly in network dynamics. Like so if you have some food webs, and then you can see, okay, how much quickly it comes to its equilibrium after a perturbation. So that's called the resilience. And also if you now introduce some invasive species in your food web or in your network, then how your network is, how much robust, or how it could resist that invasion risk. So the more the resistance, the more the stability of your network. But we are now focusing here on the variability stability concept. So we are using the community stability through time with two classic drivers. One is the species richness or the diversity, and the usual notion is that you have a positive diversity stability relationship in your community. And this is mainly due to the statistical averaging effect of more species. So if you have more species, then you will always get, as usual, a high consistent biomass throughout time. So that's called the portfolio effect. And also the second factor is the interspecific interactions. So if you have more species which are fluctuating more or less synchronously, like going up and down simultaneously at the same time, then you can say, okay, there is more synchrony, and that would add more variability in your community. So that means more synchrony means less stability. In other words, if you have more asynchronous species interaction, then you know, okay, so if we lose some species, then it could be compensated by gain of some other benefiting species, right? So it's the concept of insurance hypothesis in this system. And we can summarize this stability synchrony relationship with this variance ratio. So variance ratio is the ratio of temporal variance of your total community biomass throughout time with respect to the expected variance from an independent community. So as if no species interspecific interactions is going on in your community. They are fluctuating randomly. And if variance ratio is greater than 1, then that means there is more variability in the system, more synchronous interactions, so less stable community. If variance ratio is less than 1, then that means more asynchrony and more stable community. So that's the usual concept. Now, we have shown recently in a paper that this community stability is affected by the interspecific association in their extreme values. And we were thinking, okay, so what could cause these extreme interactions between species that are mainly coming from the extreme climatic events or some abrupt change in your system, right? So we think, okay, that means community stability should decrease if there is more association in the extreme. That was our initial thinking. And then we need to check that. So we thought, okay, we will start with these common 3 type of pairwise species interactions in a community. So one is the independent one, which is shown by the yellow dots here, where there is no interactions, no correlations between species 1 and species 2. And then we can see, okay, there is strong positive correlation between these 2 species, if that is called this synchrony. And then if those 2 species have strong negative correlation, then that's the example of asynchrony. Now, our question was that what is important that when this synchrony happens, so if that synchrony is happening when both species are rare, so both species have low values here, so that means it will cause a strong lower tail dependence between the species association, right? Similarly, if synchrony happens when both species are common, so both species have simultaneously high values, then that would cause an upper tail dependence here. Now imagine that you have a community of 13 species. So there are total 78 pairwise interactions possible in your community. So for each species pair, we first find out, okay, what is the interaction type? Is it independent or is it asynchronous? Or is it synchronous but with some tail dependence in either tail? So if there is stronger dependence in the lower tail, then that is indicated by these red shells here. The species interspecific relationship should look like figure B. And if it is blue shells, then that should be stronger dependence in the upper tail. That should look like figure C. So we compute the tail asymmetry, that is the difference between this lower tail and upper tail dependence. And then we compute the sum of all those tail asymmetry in whatever tail that is. So it is the sum of their absolute values. So it is the quantification of the tail asymmetry for a given community, right? And then we will test our model, which we divided into 4 building blocks. So the first one, we consider the stability with richness. And then with 2 classic predictors, that is the richness and synchrony, just usual synchrony with variance ratio approach. And then the last two models involves this new additional predictor where synchrony has some tail dependence. That's the total tail asymmetry. And we will ask, okay, so how this driver and stability relationship should vary between realm, that is in freshwater versus terrestrial system. And we also expect that richness should have a positive effect on stability, and also synchrony has negative effect on stability, and also tail dependence that is mainly coming from synchrony and also caused by the extreme perturbations in your community, that should also destabilize your system, right? That means the negative effect. So that's our concept behind this study. And to test these questions, we first need some data, right? And for that, we collated some open access time series, which are the time series of species abundance or biomass data for each community. So each single point on this map is presenting each community. And we use that biotime data, breeding bird survey data, and reef fish time for freshwater fishes. And also some private data, those are mainly for phytoplankton, zooplankton, or some freshwater invertebrates from collaborators. And we have used the data which are long-term data, and by long-term I mean like minimum 20 years data which were annually sampled. If they are sampled for each month in a year or some months in a year, then we took those averages to make the annual count or annual biomass. And we have these two realms, terrestrial and freshwater. We have 7 taxa, and we have total 244 study sites. So these communities, by communities I mean those are the plots which are nested within the study sites, right? So these are the hierarchical structure of the data. But there is a problem. You can see that more data are coming from the terrestrial. So it's like 75% data are coming from terrestrial. And that is mainly due to the bias of this bird data set, which is coming from breeding bird survey. So we need a way to somehow reduce this bird data, right? And for that, we used this approach, which is called stratified random sampling for birds database. So say for BBS data, there are some more or less 50-50 sampling site along a route. And there are multiple routes going through each state, right? And these are mainly from US and few are from also Canada. So those routes are also grouped in some area which is called strata, that is based on the physical habitat for the bird with different bird communities. And some stratas are big, some stratas are small. So within a big strata, there are more sampling points, and within small strata, there are less routes, so less sampling point. So we randomly sampled those data points in a way so that we can sample more from a bigger area, bigger strata, and sample less from a smaller strata. So when we did that, we reduced that data set to 1,791 communities. And here now you can see that the data set is similarly fair, like 60-40 ratio between this terrestrial and freshwater one. And it reduced the breeding bird survey data up to 21%. And we did that because we first target, okay, we should sample this amount of data from birds because that's the average of the other terrestrial organisms to make a balance between the organism of terrestrial realms. So when we did that, we then applied two inclusion criteria. The first one is that the study duration should be of minimum 20 years, and it can range up to 62 years for both realms. And then we also found that we need some species for each community which were present at least for 70% of the sampling periods. So mainly our richness is the common species which are the dominant species in that community. And why did we do that? Because we also found that recently a study published which showed that for community stability, they use that mainly the global data set for terrestrial realm, that synchrony between the dominant species matters more than the species richness. So that's why we also choose the dominant species. And then the results. So when we did not include realm, the 4 building blocks of our model shows us the expected relationship, that is the positive effect of diversity on stability, and also the negative effect of synchrony, and also including tail dependence. And then when we add the realm effect as an interaction effect on the stability, we can see, okay, so now the drivers has different effect on stability, right? Because you can see the change of the width of those arrows between freshwater and terrestrial. And even in freshwater, there are some drivers which are not at all significant effect on this stability. So we got this result from this hierarchical Bayesian setup where we used this richness, variance ratio, and tail asymmetry as predictors to interpret the variation in the response variable stability. And we also used the random effect for random intercept due to the study sites, due to the plots which are nested within study site, and study sites are also nested within taxa. So then we need to interpret these results, right? So we made a table which can compare the performance score between these 8 models, 4 including realm and 4 without realm. And from this result, okay, we also used the common estimates to measure this performance score. The R-square values, which are in general represent the how much the variation in your response variable is due to all those effects like fixed effect and random effects, and then marginal R-square, that is only due to the fixed effect, that is the predictors here. And also there is some standard root mean square error, RMSE, and some information criteria, Lewis statistic, and also weighted AIC, and some expected log likelihood of probability density. So based on all these common estimates, we have found our result that asymmetry matters, even if you include realm or not. So whenever you see that there is an asymmetry in that as a predictor variable, you can see there are higher performance score than the models which did not include asymmetry, right? Similarly, we can also see that asymmetric interaction effects were more prominent here for terrestrial realm than the freshwater one. And that could be explained by, like, for terrestrial realms, you have more heterogeneity in habitats, right? So there would be more extreme climatic events. But for freshwater, in aquatic system, there are more homogeneous. So they can buffer easily any change in the environment. So for example, I think in 2019 maybe, there was a study which showed that rising temperature effect was buffered in marine and in freshwater realm, but not that much in terrestrial. So then the second result, we also found that, okay, realm matters because the stability for terrestrial was also higher than the freshwater one, if you just compare the intercepts. And also whenever you add the realm effect in your model with a given predictor, then always it increased that performance score. And then the second thing we find that the diversity and variance ratio effect on stability were greater in terrestrial realm. This is because there is an inherent gradient in richness, right? Because terrestrial realms are more species rich, because we know that from this heterogeneity in habitat and with this richness relationship mostly shows the positive slope, right? So if there is more climatic niche in terrestrial ring, then that means more species rich it will be. So that would also increase the community stability by portfolio effect. Similarly, in our data, we have found that there is more synchrony versus asynchrony for freshwater realm, which decreases the stability of freshwater communities than terrestrial ones. Now we also ask the question, okay, so there is a difference, but are the differences significant between realms? So to answer that questions, we here plot the estimates for median and 75% and 95% CI for the posterior estimates from that model. And the gray line here is showing the difference between the terrestrial and freshwater one. And if that gray line touches this vertical line, that means there is no significant difference. So for richness and variance ratio, the difference was strongly significant, but for intercept and for total tail asymmetry, the difference was moderately significant based on 75% CI. And in figure E, you can see the effect size of different taxa. So for freshwater, we can see there is a consistent and significant negative trend. But for terrestrial one, the trend is not that much significant. And also, this is only coming from that random effects, right? But we did not include that taxa as a fixed effect. So to study that, we need more consistent number of sampling size across taxa, so that then we can compare between taxa. So the take home message is that the realm matters because stability is different for terrestrial versus freshwater communities. And also freshwater communities are less stable than terrestrial ones. The diversity stability positive relationship and the synchrony stability negative relationship are much stronger in terrestrial. And also due to ongoing climate change and also for the extreme events, the asymmetric interactions play important role for community stability, being more prominent in terrestrial ones. And we can link these synchrony patterns with stability, and we can consider the basic difference between realms to offer new avenues for explaining community stability and call for rethinking conservation efforts across realms. So finally, I would like to acknowledge my supervisor, Catherine and Blake, and also the other contributors for this project and for funding the BGB Research Initiative 2020 and ERC Advanced Grant. And thanks to all of you. If you have any questions, collaboration, data, you can reach out to me. Thanks.
Thank you, Shyamolina.